The atomic concept proposed by Democritus, a pre-Socratic philosopher from ancient Greece, represents one of the most profound and far-reaching ideas in the history of science. His theory of the atom, though speculative and without empirical evidence at the time, has been foundational in shaping our modern understanding of matter and the physical universe. In this essay, we will explore the reasons why Democritus's atomic theory is regarded as a landmark in the field of physics, examining its historical context, its theoretical contributions, and its lasting influence on the development of scientific thought. Historical context of Democritus's atomic theory. Before Democritus, the dominant view in ancient Greek philosophy was that matter was continuous, meaning it could be divided indefinitely into smaller parts. This idea was held by philosophers like Heraclitus, who believed that everything was in a constant state of flux, and Pythagoras, who focused on the relationship between numbers and the cosmos. These early thinkers did not have a clear notion of atoms or indivisible particles. However, Democritus and his mentor Leucippus proposed a radically different idea, that matter is made up of indivisible particles, which they called atomos, Greek for uncuttable or indivisible. This was an extraordinary leap of imagination. Democritus's concept was not based on experimental evidence, but rather on deductive reasoning and philosophical thought. Despite being largely ignored or rejected by his contemporaries, the idea of atoms would lay the foundation for centuries of scientific inquiry into the nature of matter. Core ideas of Democritus's atomic theory. Democritus's atomic theory was grounded in a few central ideas that were revolutionary at the time. Indivisibility of atoms. At the heart of Democritus's atomic theory was the belief that all matter is composed of tiny, indivisible particles. These atoms were considered to be the smallest possible units of matter, and they could not be divided further. This concept of indivisibility was based on the observation that matter could be cut or divided into smaller parts, but at some point, there must exist a smallest part that could not be further divided. The nature of atoms. Democritus described atoms as being eternal and unchanging, in contrast to the physical objects they composed. Atoms were thought to be in constant motion, colliding with one another, and this motion determined the properties of matter. The atoms themselves were characterized by different shapes, sizes, and arrangements, and these differences gave rise to the various properties of materials in the macroscopic world. Void and motion. According to Democritus, the void, or empty space, existed between atoms. This was a crucial idea, as it allowed atoms to move and interact with one another. The void was not a nothingness, but a space where motion could occur. Without the void, there could be no motion, and thus no change in matter. The motion of atoms within the void accounted for the changes and phenomena observed in the physical world. Determinism in nature. For Democritus, all phenomena in the universe were the result of deterministic interactions between atoms. In his view, the behavior of matter was governed by the motion and interactions of these atoms according to fixed natural laws. This mechanistic view of the universe was in contrast to the more mystical or divine explanations that prevailed at the time. Philosophical implications of the atomic theory. Democritus's atomic theory was not just a scientific idea, but a philosophical one. It had profound implications for how humans understood the universe and their place within it. Materialism and naturalism. Democritus is often considered a materialist, meaning he believed that everything that exists is made of matter and is subject to natural laws. His atomic theory challenged the more mystical or supernatural explanations for natural phenomena. In his view, The universe could be understood as a system of interacting particles governed by the laws of nature, not by divine intervention or mythological forces. This was a radical departure from religious or spiritual explanations of the cosmos and laid the groundwork for later developments in natural science. Causality and reductionism. Democritus's idea of the atom also implied a reductionist view of nature. He suggested that all complex phenomena, from the movement of planets to the formation of living organisms, could ultimately be explained by the behavior of atoms. This reductionist approach to science, which seeks to explain complex systems in terms of their simplest components, would become a central method in modern physics and biology. Materialistic ethics. Democritus also applied his materialistic worldview to ethics and human behavior. He believed that human experiences, such as pleasure and pain, were the result of the interactions of atoms within the body and mind. His materialist ethics emphasized the pursuit of happiness through moderation and self-control, avoiding excess and living in harmony with the natural world. Despite the radical nature of Democritus's atomic theory, it was largely ignored or rejected by many philosophers of his time. The most notable critic of the atomic theory was Plato, who advocated for a more idealistic view of the universe. Plato's theory of forms suggested that the physical world was a mere shadow of a higher, unchanging reality of abstract forms or ideas. Aristotle also rejected the idea of indivisible atoms, favoring a more continuous model of matter based on his own theory of the four elements: earth, air, fire, and water. The prevailing philosophy in ancient Greece was often more metaphysical and speculative, focusing on abstract concepts and ideal forms rather than empirical observation and experimentation. As a result, Democritus's atomic theory did not gain widespread acceptance in the ancient world. Although Democritus's ideas did not gain traction in his own time, they were rediscovered and revived centuries later. The first major revival of atomic theory came during the Renaissance, when philosophers and scientists began to challenge the dogma of ancient Greek thought and develop new approaches to understanding the natural world. During the scientific revolution in the 16th and 17th centuries, scholars like Galileo Galilei, Johannes Kepler, and Isaac Newton laid the foundations of modern science, which emphasized observation, experimentation, and mathematical reasoning. These ideas encouraged a re-evaluation of ancient theories, including Democritus's atomic concept. In the early 19th century, the English chemist John Dalton developed the first modern atomic theory based on empirical evidence. Dalton's theory, which was influenced by Democritus's concept of indivisible particles, stated that each element is composed of atoms of a single, unique type, and that chemical reactions involve the rearrangement of these atoms. Dalton's work, along with the later discoveries of atomic structure and the periodic table, helped to establish the atom as the fundamental building block of matter. In the 20th century, the development of quantum mechanics and the discovery of subatomic particles further revolutionized our understanding of the atom. Albert Einstein's theory of relativity, Niels Bohr's model of the atom, and the development of quantum field theory all built upon the idea that matter is composed of discrete, fundamental units, even though the atom itself is not indivisible in the strict sense. Democritus's atomic theory is considered a landmark in physics because it set the stage for the development of atomic theory, which is central to nearly every branch of modern science. Modern physics, particularly quantum mechanics and particle physics, builds upon the notion of atoms and subatomic particles. The discovery of the electron by J.J. Thomson, the proton by Ernest Rutherford, and the neutron by James Chadwick further refined our understanding of the structure of the atom. Quantum mechanics, which governs the behavior of particles at very small scales, has its roots in the concept of discrete, fundamental units of matter. The understanding of atomic and subatomic particles has led to numerous technological innovations, from the development of semiconductors and lasers to medical imaging techniques like MRI and PET scans. The applications of atomic theory in technology and medicine have transformed the way we live and interact with the world. The idea of discrete particles is also central to our understanding of the universe at large. In cosmology, the study of the early universe and the behavior of elementary particles in high-energy environments is based on the principles of atomic and particle physics. The standard model of particle physics, which describes the fundamental forces and particles of the universe, owes its foundations to the atomic theory. Democritus's atomic concept, although speculative and unproven in his time, was a groundbreaking idea that transformed our understanding of the nature of matter. His notion of indivisible particles as the building blocks of all matter provided a conceptual framework that would be revisited and expanded upon in the centuries to come. While the atomic theory,